Okay, so welcome back to part 2 of this section 5.3. Last time we were talking about the Fundamental Theorem of Calculus, part 1, which said if you have a continuous function on a closed interval and you define g of x to be this integral from a to x f of x dx, f of t dt, then g is continuous, and then also what do you have? Well, you have that the derivative of g is f. So let's think about this statement a little bit more deeper. If we have some sort of graph for the integral, let's say it goes up to around here, and then goes down with a min, and then goes up a little bit before it levels off. And that's the integral. What does the original function look like? Well, to get the original function, I need to look at the derivative. I have that it's a whole bunch of positive values on here, right? Because it's increasing until at this point I should get 0. Because that's a maximum. So let's say something like this. And then over here I have a minimum, so my original function should be 0. And that's maybe something like that. And then it increases slightly before it levels off. With that sharp corner, so that's why you have this jump here. So that's the original. And how did we go about saying that? Well, to get the original from the integral, I took a derivative. We have a word for that we talked about previously. It's been a couple sections. But what that was that g is an antiderivative of f. And that's where we're going to get started with part 2 of the Fundamental Theorem of Calculus. What does part 2 say? Well, you still have f continuous on closed AB. But then part 2 says then we can actually evaluate what this integral is. And we don't have to do Riemann sums at all. It's just capital F of B minus capital F of A, where f is an antiderivative of little f. So one thing I notice is that how is this definition consistent? Because remember, there are multiple antiderivatives. But remember, if f and g are two antiderivatives of the same function, then f of x equals g of x plus just some constant. So what happens to constants? whenever you look at this definition? Well, f of b minus f of a, using that g of b plus c, it'd be g of b plus c minus g of a plus c, which, after you distribute the negative, that's going to be g of b minus g of a, because the c's cancel. So, no matter which antiderivative we choose, we'll always get this same number. So this thing actually is defined in a way that makes sense. Although, I will say, thinking about the Fundamental Theorem of Calculus, it's a really big deal because, for one, we don't have to go back to looking at Riemann sums, except maybe on a test if I ask you. But also, we've talked this entire semester about taking derivatives, and what the Fundamental Theorem of Calculus Part 2 says is there's actually a relationship between them. Between Part 1 and Part 2, what does it say? Well, if you have differentiation, that's taking a derivative. You have integration, taking an integral. Those are inverses of each other. Similar to how addition and subtraction are inverses, or multiplication and division, how one undoes the other. Now, I will say, in practice, integration can feel a little bit more challenging than differentiation. So if you get frustrated at first with integration, don't give up. It's just what happens sometimes when you look at integrals, is that they tend to be a little bit more challenging. But we have this nice formula here, this on how to compute the integral. So for the rest of the time, I would just like to do a couple examples to just see this in practice. Okay, so let's erase this top and write down this. The Fundamental Theorem of Calculus Part 2. Okay. So the first example, evaluate this integral. Well, what is my antiderivative that I'm going to use? Well, my antiderivative will be, it's the power rule for antiderivatives, says you add 1 to the power, and then you divide by the new power. So this is x cubed over 3, and then 2x goes to 2x squared over 2, and then minus 4x. And then the most general antiderivative would include this plus c, because it could be any constant that you could have there. I could have 1, I could have 5, I could have 10, I could have negative 100. Depends on which one I want to choose. In general, for these problems, for doing definite integrals, a little hint is, to make your computations easier, try c equals 0. You get to choose which one you want to use. So we'll just use the one where this is 0. Makes our life a lot nicer. Okay, so what does that give us? Well, by the Fundamental Theorem of Calculus Part 2, this is going to be f of 3 minus f of 1. Or the notation we'll sometimes write it is we'll write out this full function, the x cubed over 3 plus, cancel these to get x squared minus 4x, and then we'll put bar 1, 3 to say evaluate it first at 3 and then subtract evaluating it at 1. And what do we get? Well, let's clear some space here. We're going to get, first term is going to be 3 cubed over 3 plus 3 squared minus 4 times 3. And putting big parentheses to remember that I'm going to need to distribute this subtraction. 1 cubed over 3 plus 1 squared minus 4 times 1. And you can compute that in your calculator. And what will you get? Well, this will be 26 over 3. Or just under 9. It's like 8.66 repeating. So that's one example with a polynomial. Let's continue and do more examples. What about from 1 to 9 of square root of x dx? Well, as is, we can't really do this one, but we can rewrite this as x to the 1/2 power dx. And then now we can use that power rule for antidifferentiation to give us that you add 1 to the power and divide by the new power. And then we do this notation where bar 1, 9, saying we're going to evaluate it at 9 first and then subtract evaluating at 1. So what does that look like? Well, this becomes 2/3 9 to the 3/2 minus 2/3 1 to the 3/2. Put that in your calculator. You'll get 2/3 times 27 minus 2/3 times 1, which is 52/3. Okay, so we just keep on doing these examples. Let's get practice. There will also be a worksheet today to help you get more practice. Okay, so let's look at -5 to 5 e dx. Well, think, what's the antiderivative of e, which is a number? That's going to be e times x from -5 to 5. Or 5 times e minus -5 times e, or 10 times e. Don't be thrown off by the fact that there's e. E is just a number, similar to pi. Okay. Now let's look at this integral. Okay, so let's look and see, well, what's the antiderivative of x to the fourth, 1 over x to the fourth? Well, that's x to the negative fourth, so it's x to the negative 3 over negative 3, evaluated from negative 2 to 2. And this is going to be negative 1/3, 1/8 minus negative 1/3 times 1/8. And what do we get? Well, this is going to be negative 1 over 24. And then, oh, I apologize. That should be a negative 8. So then it's plus negative 1 over 24 or negative 1/12. Now that looks fine, but remember what the function 1 over x to the fourth looks like. It's always lying above the x-axis. So this number actually doesn't make any sense. Now, why doesn't it? What went wrong in getting this in this non-example? Well, remember, the fundamental theorem of calculus is only for continuous functions. Is 1 over x to the fourth continuous on negative 2 to 2? It is not, because it has a asymptote at 0. Right? You have this vertical asymptote. So this integral actually will not exist. So let's go back to doing examples instead of looking at that non-example. Although that non-example really does show you that you need to be careful. Is the function you're looking at continuous on whatever you're looking, that open interval you're looking at, or is it not? And if it's not continuous, can you somehow split it up? Okay, so let's look at this integral. We're going to look at a piecewise function. It's going to be sine, and then it's going to be cosine. And this is going to be, this one is on 0 less than or equal to x, strictly less than pi over 2. And this one is for pi over 2 less than or equal to x, less than or equal to pi. How do we integrate this thing? It's a piecewise function. Well, remember our properties of integrals. Those are going to be making a comeback now, is talking about these properties of integrals. I can split this up into the integral from 0 to pi over 2 f of x dx plus the integral from pi over 2 to pi f of x dx. Okay, so why can I do that? Well, property of integral says if I make this number and this number the same, I can split it up in this way, thinking about it as splitting it up into two parts. But that's going to be 0 to pi over 2 of sine x dx plus pi over 2 to pi cosine x dx. We can do that because of how this function is defined. Okay? Take its antiderivative. What do you get? Well, in the first one, the antiderivative of sine is negative cosine. Remember that negative sign. And then we evaluate it from 0 to pi over 2. And then it's plus, the antiderivative of cosine is sine, evaluated from pi over 2 to pi. And you could do this calculation. What will you get? Well, it's negative cosine of pi over 2 is 0 minus negative cosine of 0 is 1. So that was from this first term. Plus sine of pi is going to be 0 minus sine of pi over 2 is 1. Or we will get 1 minus 1 or 0 for this integral. So that's just like split it up and do this integral. Okay, so there is a worksheet in that I would want you all to work on in Canvas, but that is all we will talk about for the Fundamental Theorem of Calculus for this section. But so that tomorrow we can move on to the next section, talking about what are called indefinite integrals. So I will see you all then.